This is the last part of the linear algebra section of this course, and in this lecture we are going to discuss symmetric matrices. Now, symmetric matrices appear in almost every engineering discipline, and they really make solving problems much easier. So, a symmetric matrix is a matrix whose off-diagonal components are symmetric. So, if I have a matrix S, let's say in a 3, that's 3 by 3. If Sij is equal to Sji, then S is symmetric. Or in other words, S is equal to H transpose. So basically the matrix would look like this. Now this definition applies in fact for any n by n matrix. Now if S is a 3 by 3 matrix, then S has the following form. S will be equal to S11, S12, S13, S22, S23, S33. Now because it's symmetric, this number is repeated here, this number is repeated here, and this number is repeated here. So this will be S23, S13, S12. So why is it why does it make things easier? Because of the following fact. Whenever I have a system that is or a matrix that is symmetric, so let's say I have a certain coordinate system made out of E1, E2, and E3, and I have a symmetric matrix here, S11, S12, S22, S33. Then there is another coordinate system. I'm going to call it P, Q, R. There is another coordinate system where this symmetric matrix can be expressed in a diagonal form. S1, S2, S3, and the rest are zeros. This is a fact that only exists in symmetric matrices, and this fact allows us to find physical quantities that we're going to discuss in later chapters, such as the principal stresses and principal strains. So whenever I have a matrix that's symmetric, I'm always looking for the other coordinate system in which, once I translate this matrix from the language of this original coordinate system to the language of this new coordinate system, the new expression of the matrix is diagonal, and the off-diagonal components are equal to 0. Now this fact is necessarily true only for symmetric matrices. So let's try to understand the reason behind this fact. Why is this true? The reason it's true is because of the following statement that you must never forget. This statement states a symmetric matrix S, or a matrix S, is symmetric if and only if it's equivalent to saying it has 3 real eigenvalues and it is possible to choose 3 corresponding orthonormal eigenvectors. So what this means is the following. So there's a proof in the book, and you should read the proof and try to understand the proof. But I'm not going to cover the proof now. I'm just going to show you an example. S belongs to 2 by 2, the space of 2 by 2 matrices. S is symmetric, which means S has this form: S11, S22, S12, S12. Let's try to find its eigenvalues. So to find the eigenvalues, we would say the determinant of the matrix S minus lambda I is equal to 0, which means S11 minus lambda 0, S12, S12, it's symmetric, so the off-diagonal components are the same. S22 minus lambda, this is equal to S minus lambda I. Now the determinant of S minus lambda I is equal to S11 minus lambda, S22 minus lambda, minus S12 squared, and I want this to be equal to 0. If you rearrange, you will get S11 S22 minus lambda S11 plus S22 plus lambda squared minus S12 squared equals 0. From which, if you utilize the famous formula for the quadratic equation for lambda, you'll find that lambda is equal to S11 plus S22 plus or minus S11 plus S22 squared plus 4 S12 squared minus 4 S12 S11 S22 all of this divided by 2, and if you look at the expression under the square root, this is always real because what's under the square root is always positive. What's under the square root, s11 plus s22 squared plus 4 s12 squared minus 4 s11 s22 is in fact equal to s11 minus s22 squared plus 4 s12 squared, which is always greater than 0 or equal, because this is a positive number and this is a positive number, so lambda is greater than 0. Now, of course, in this example, we used S as a member of a 2 by 2 matrix, as a member of the set of matrices that are square and with dimensions 2. If you try to do this for a larger matrix that's n by n, the equation will be very complicated, and you should check the simpler proof that's presented in your book. So for higher dimensions, i.e. S is a matrix that's n by n, use the proof in the book. Okay, so let's try to understand now how we can choose the eigenvectors or the eigenvalues and the eigenvectors of a symmetric matrix, and why we say that the eigenvectors are always orthonormal. So let's look at examples. First one is the matrix Pi. So consider the matrix M. It's a diagonal matrix. In fact, it's equal to P 0 0 0 P 0 0 0 P. P is a real number and I is the identity matrix, and so the matrix M is equal to Pi. Now, if you write the equation, the determinant of M minus lambda I is 0, you will get P minus lambda cubed equals 0, from which you get that lambda equal P. So we've got 3 eigenvalues, each is equal to P. Now, so this is for the eigenvalues. Now for eigenvectors, we are looking for vectors x, which when I multiply by m, I get the same vector x, maybe a little bit bigger or smaller. Now, they have the same directions, but slightly scaled by the factor lambda. So what you notice is, because of how the matrix M is formed, mx is in fact equal to a number multiplied by I multiplied by the vector x. Ix is in fact Px, which means that any vector x is indeed an eigenvector of M. Now we need to choose 3 different eigenvectors associated with the 3 eigenvalues P. So you can choose, because any vector is eigenvector, I can choose eigenvector 1 equal to the vector 1 0 0, eigenvector 2 to be equal to 0 1 0, eigenvector 3 to be equal to 0, 0, 1, from which you see that eigenvector 1. So from this you see that the eigenvectors are orthonormal. Each has a length of 1 and they're all perpendicular to each other. Okay, so this is the first example. You will find a few other examples in your book. The next thing here is the spectral decomposition of a symmetric matrix. The spectral decomposition of a symmetric matrix refers to the fact that if there is a coordinate system E1, E2, and E3 in which a matrix S is symmetric, I can find another coordinate system in which the new matrix S, or the representation of S in this new system, is diagonal. And of course we know that there's a translation matrix here that's equal to Q, as we studied in the previous part. Now the question is, what is this coordinate system and how can I find it? So given a symmetric matrix, what is the coordinate system in which this matrix representation is diagonal, and what is this Q? So let's use the results from the previous statement. If S is symmetric matrix, then and S is a 3 by 3 matrix, then we can find P, Q, R, 3 vectors that are the eigenvectors of S, and P, Q, R are orthonormal. So they are perpendicular to each other, the size of each is 1, and they are the eigenvectors of S. Then let's do the following operation. I know if I multiply S by P, which is made out of P1, P2, P3, what do I get? Well, I know that SP, I'm just going to write here, SP is equal to lambda P, which means when I multiply S by the components of P, I get the components of P again, but multiplied by a number lambda 1. But that's the same for Q as well. I'm going to get Q1, Q2, and Q3 multiplied by lambda 2, the second eigenvalue of S. And the same for the third eigenvector, SR is equal to lambda 3R. I'm going to get R1, R2, R3. So when I multiply the matrix S by the vector P, I get the vector P again multiplied by a number lambda 1. When I multiply the matrix S by Q, I get the vector Q again, multiply by a number lambda 2. And when I multiply S by the vector R, I get R again, multiplied by lambda 3. Now since P, Q, and R are ortho normal, then Q, that's made out of P1, P2, P3, Q1, Q2, Q3, R1, R2, R3, is an orthogonal matrix, as we studied in the previous part. Therefore, in fact, you see that the above matrix equation can be written like this: S Q transpose is equal to Q transpose multiplied by S prime. Now, since Q is an orthogonal matrix, the inverse of Q is equal to Q transpose, which means that S prime, which is the diagonal representation of S, and it's made out of the eigenvalues of S, can be written as a matrix Q multiplied by the original S multiplied by Q transpose, where Q is a matrix of the eigenvectors of S. And this makes the calculation of the principal invariance of a symmetric matrix really easy. Because if I have a symmetric matrix S that's made out of S11, S12, S22, S33, S23, S13, and a number here, number here, number here, there is a coordinate system in which S prime is equal to lambda 1, 0, 0, 0, lambda 2, 0. So this is the same matrix but represented in a different coordinate system, and thus becomes diagonal. In the first invariant of S, which is the sum of the diagonal components, instead of calculating it in this coordinate system, since it's invariant, I can calculate it in the new coordinate system. So I1 of S is equal to I1 of S prime. I can say it's equal to the sum of the eigenvalues. I2 of S is equal to I2 of S prime, which becomes very easy for a diagonal matrix. It's equal to lambda 1, lambda 2, plus lambda 1, lambda 3, plus lambda 2, lambda 3. And I3 of S, which is equal to I3 of S prime, because the invariant is indifferent whether you calculate it in the original coordinate system or in the new coordinate system. This will be equal to the determinant of S prime, which is equal to lambda 1, lambda 2, lambda 3. Okay, so this is the theoretical part about the symmetric matrix. Let's try to visualize what all this means. And we're going to view this in a two-dimensional vector space. So let's assume S is a symmetric matrix in a two-dimensional vector space. S is symmetric. Since S is symmetric, it possesses two perpendicular eigenvectors. And we know, so P and Q are orthonormal eigenvectors of S. What does this mean? It means that SP, when I multiply S by P, I get P, but multiplied by a number 1. And when I multiply by S by Q, I get lambda 2 multiplied by Q. Which graphically means, if this is P, once I apply s to the vector p, I get perhaps it's in the same direction, but perhaps a little bit longer. Of course, s multiplied by negative p, because it's a linear map, s multiplied by negative p is equal to negative lambda 1 multiplied by p, and s multiplied by q may be the same length, or maybe shorter, or maybe slightly longer, and in the opposite direction I get the opposite direction, which means that because s is symmetric, it represents extension in the direction of the eigenvectors, of its eigenvectors. So s extends or contracts its eigenvectors. And if my coordinate system is in fact this coordinate system, PQ, then S prime would look like this: lambda 1, 0, 0, lambda 2. And it would of course do the same action. This is my circle. Then when I multiply S prime by the vectors in this circle, I will get this ellipse, but will be aligned with the coordinate system. So let's just give you a counterexample so that you understand that this is not true for any matrix. This is true only for symmetric matrices. So let's find a matrix that does not do that. And that's a very simple example. Let's say Q, a matrix that's equal to cosine 30, negative sine 30, sine 30, cosine 30. So this is a counterexample. So what does this matrix do? Well, it rotates any vector by an angle 30 degree. So this is the original direction vectors, all the vectors in any direction. After I apply Q, this vector rotates 30 degrees. This blue vector rotates 30 degrees. This red vector rotates 30 degrees. And so vectors are always rotating. Qx is never equal to lambda x, i.e. you can never find a vector x such that Qx equal lambda x. And of course you can never find a vector x that's not equal to the 0 vector, because in the 0 vector Q multiplied by 0 is equal to lambda multiplied by 0. So we don't really look at the 0 vector, we just look at any vector that's not 0, such that when I multiply Q by this vector, I get the same I get the vector in the same direction but rotated. So the last example in this section just to give you a numerical example, we need to find a coordinate system in which the following symmetric matrix is diagonal. So let's look at what we have here. In this coordinate system, E1, E2, and E3, M has this representation. There is another coordinate system somewhere that's made out of the principal, the eigenvectors of M. In this coordinate system, M prime, which is equal to Q M Q transpose, and Q is this matrix of translation between the two coordinate systems. This M, or this Q, M prime will be a diagonal matrix. So let's find all those values. So the first thing we have to do is, what are the eigenvalues and eigenvectors of M? Okay, so we form the new matrix M minus lambda I, and we say that the determinant of this matrix has to be 0, which means we make this matrix not invertible. And from here, if you do the calculation, and you don't have to do the calculation by hand, you should know how to do it, but you don't have to do it for the assignments. You can use the software Mathematica, as I will show you. So this is the solution, the three eigenvalues. Associated with lambda 1, you get the eigenvector P, which will be equal to 0.68, 0.18, 0.71. Associated with lambda 2, you get a Q, which is equal to negative 0.68, 0.5, 0.53. And associated with the third eigenvalue is the third eigenvector R, which is equal to negative 0.26, negative 0.85, 0.47. Now you always need to verify that P dot Q is equal to Q dot R is equal to P dot R is equal to 0, and P dot P has to be equal to Q dot Q has to be equal to R dot R equal to 1. Orthonormal. Then you form your Q, which is the representation of P, Q, and R in the original coordinate system. This is the matrix of translation between the two coordinate systems. So this is P1, P2, P3, Q1, Q2, Q3, R1, R2, R3, which is equal to 0.68, 0.18, 0.71, negative 0.68, 0.5, 0.53, negative 0.26, negative 0.85, 0.47. So this is the translation between the two coordinate systems. We know what M is. M prime will be equal to Q M Q transpose. If you do this calculation, lo and behold, you get 4.640, negative 2.797, 0. You get a diagonal matrix. And what are the values of these diagonal components? They are your actual eigen values of the matrix M. And so this example shows you how to form Q, which is the translation between the matrix, the coordinate system, the general coordinate system that we're using for the symmetric matrix, and the new coordinate system in which the matrix becomes symmetric, and this new coordinate system is made out of the eigenvectors of the matrix N. Okay, so the last section in this part, and this is not going to be covered in your midterm, is what we call positive definite and semi-positive definite symmetric matrices. So let's understand why we need to study something like this. So in general, I have in any mechanical system, in general, I have a force vector. So I'm going to say that this force vector belongs to an n by n an n Euclidean vector space, n-dimensional Euclidean vector space, and this force vector produces a displacement vector in an n by n dimensional vector space. And from elasticity, I can find a symmetric matrix where this vector f is equal to a matrix, an n by n matrix, multiplied by this vector delta. And usually in mechanical elastic systems, this S is symmetric. So what happens when I multiply? If I want to get the energy of the system, the energy, as you know, is equal to F dot delta. F dot delta is equal to S. F is equal to S delta. Now the energy of deformation is always greater than or equal to 0. Which means, of course, this applies for any delta. Any deformation, the energy that goes into the deformation of the system has to be greater than or equal to 0, which poses some restrictions on S. And the restrictions are called S has to be positive definite or semi-positive definite. So a positive definite matrix is defined as follows: S is an n by n matrix, S is symmetric, so the definition of positive definite. For every u in Rn, u is not the zero vector, Su dot u, the energy, if you want to call it the energy, has to be greater than 0. Semi-positive definite. And here I don't have to put that restriction because I can say Su dot u can be equal to 0, but always greater. So greater than or equal to 0. If this is true for any vector, S is called semi-positive definite. So what does this mean? It means that, or what does this lead? It always leads to the following: that the eigenvectors of S, or the eigenvalues of S, when it is positive definite have to be greater than 0. So basically S prime lambda 1 0 0 0 lambda 3 0 and so on, all the lambda I have to be greater than 0. And this concludes our linear algebra part. I'm going to show you some, in the next videos, I'm going to show you how to do all this using Mathematica. And after that, we're going to start the mechanics part of this course.